This is the third in a set of 4 videos on the analysis of categorical data, or basically inference for counts and proportions. In the previous video, we talked about drawing inferences about differences in proportions between two or more groups. And in this section, we're going to talk about a related topic called Simpsons Paradox. That is, in drawing conclusions or inferences based upon nominal data, it is actually quite common for analysts to draw paradoxical or just flat out wrong conclusions. And this occurs because they fail to consider all the possible variables that may be coming into play in the observed behavior of the population of interest, or populations of interest, depending on the problem. I'll give you an example. According to World Health Organization statistics, the people of Sweden are among the healthiest in the world. A very healthy, excellent healthcare system. Yet, in any one year, the probability of dying is higher in Sweden than many third world countries with poor healthcare systems. Well, this seems paradoxical, and it is. The problem is that I considered the probability of dying in Sweden and then compared it to other countries, but I didn't take into account age groups. It turns out, yes, the Swedes are very healthy. They're also an old population, while the population of third world countries is younger. Therefore, the probability of dying is actually higher in Sweden, but that's simply because people are older. So failure to consider age in terms of the probability of dying led to an incorrect conclusion. And in fact, by age group, the probability of dying is very low in Sweden compared to many other countries, especially third world countries. So I'm going to illustrate Simpsons Paradox with an example. And we're going to look at a data set called disease. So this is a serious illness, and we won't say what the illness is in this case, that people can contract. And there are 2 treatments. There is a traditional treatment, or usual, and there is a new treatment that is being tested, which they believe may have a higher survival rate or be better. So basically, on the next slide, and we'll do this in jump in a moment, we look at the treatments. So on slide 22, I have the new treatment and the usual treatment and whether the person died or survived. So notice with the new treatment, if you look at the table, 89% died, 11% roughly survived. So you'd say, well, clearly we'd want the usual treatment because only 55% died. You're going to see in a moment this is a completely incorrect conclusion. And why? Well, let's go back and look. What have we ignored? The stage of the disease. So some of the people in the treatment study are in an advanced stage, some are in the initial, and we have no idea how the advanced and initial subjects have been allocated to the treatment groups. So let's go over to jump and take a look at the data. So here's the data in cross-tabulated form, so keep track of the count column. So I will first go to the Analyze menu, fit Y by X. I will make treatment X and the outcome Y. We're interested for the different treatments, what are the outcomes? Both are nominal, and I'll put count in the frequency box. Okay. So notice just from the mosaic plot, okay, I'm going to go ahead and label these as show percents. So from these, it would appear that you'd much rather have the current or usual treatment because only 55% died. Again, I'm going to simplify the contingency table display. Okay. Notice something interesting. There are, in the entire study, 19,100 people. Okay. And notice for the new treatment, there are a little over 10,100 to be specific, and 9,000 the other. We take a look at the chi-square test, and it says, yes, this difference we're observing is real. Okay, so it appears there is a real difference between the two treatments. However, we may not have reached the right conclusion that the usual treatment is preferred because we've overlooked something. That is the disease status of the patients. So I'm going to redo the analysis. So I'm going back to fit y by x. I'll hit recall. But notice the by box. I'm going to do the analysis by disease. So I'm going to do it for initial and advanced. I'm going to do a separate analysis and then see under those conditions how the treatments relate to the outcomes. Okay. So for the first case, this is where people were in the advanced stages. Again, I'll simplify the display. Notice for advanced, for the new treatment, there were 10,000 subjects and only 1,000 for the usual. This actually would make some sense because if the usual treatment had a high risk of death if you're advanced, doctors might be more likely to put you in the new treatment hoping for better outcomes. Now let's look at the percentage that died. These are high, but again, this is a lethal illness and few people survive once they're in the advanced stage. But overall, it does appear that the new treatment has a lower death rate, or rather, you could say has a higher survival rate, twice as high. And from the Pearson test, this appears to be correct. So now let's look at the initial. Again, I'll simplify the contingency table so it's easier to read. Notice in the initial stage, only 100. Notice the imbalance. This is actually very poor as a study design. So we had 10,000 getting the new treatment that are advanced and only 1,000, or 100 rather, getting the new. In the usual treatment, we have a high proportion of patients. Here's the problem. What's happened is disease, initial or advanced, partly because of the poor study design, is completely confounded with the treatments. Again, it's a very poor design, but it makes the point about Simpsons Paradox. Once again, notice in the initial stages, there is no doubt the new treatment is far superior. So once I take into account whether or not they're advanced or initial, this is a third variable, we suddenly discover that actually the new treatment is best in both cases, while when we ignored the disease state, we came to the conclusion the usual were better. And this is called Simpsons Paradox. It comes about because we simply ignored other variables that might have an impact on the relationship between the two nominal variables, treatment and outcome. It's a very common problem, happens all the time. Okay, especially with nominal data because it has so little information or context. So the bottom line to Simpsons Paradox, and this is discussed in the notes, it'll step you through the analysis, is the fact, and I'll show you this on slide 26, the moral is never to generalize from data counts that have been grouped across categories without first understanding the relationships within the categories. There are various types of analysis we could do here, but they're beyond the scope of this level of course. I just want to warn you, Simpsons Paradox is real, it commonly occurs, and you must be vigilant in the analysis of nominal data to spot it when it occurs.